everyone. I hope you all are having great time at DevOps Days. There have been a lot of great talks, and I believe there was an open space related to burnout and mental health. So my talk is along the same lines, but from the technical perspective. I know this is the last talk of the conference, so I'll try to keep it short. And without further ado, let's get started. My name is Monika, and I work as Systems Reliability Engineer at Cloudflare and in Observability team. Observability is to provide visibility into the technology stack by collecting and analyzing wider range of data. In this talk, I'm going to talk about alert observability. This will look familiar to a lot of you. Yeah, this is fine. This is how a typical day for a lot of on-calls look like. On-calls receive a lot of alerts. Receiving too many alerts can lead to alert fatigue. Alert fatigue is essentially exhaustion caused by responding to unprioritized and unactionable alerts. Talking about on-call, I am on-call 24/7, 365 days a year, being a mom to a toddler. And talk to me about toddler alert fatigue. I can talk about all day long. It's 2 a.m. at night. Your kid wakes you up. Hey, wake up. I'm hungry. I generally suggest kid to drink some water and go back to sleep, just to make sure he's really hungry and not dreaming that he's hungry. Well, similarly, in the case of alerts, we want to make sure that the alerts are accurate and not false positive. Receiving false positive alerts can desensitize on-call person. There have been several studies conducted to investigate health impacts of on-call work or similar work schedules such as night shifts or rotating shifts. These studies are especially common in relation to fields like healthcare, where on-call schedules are prevalent. Here are some of the general findings. Being on-call can lead to irregular sleep patterns, potentially leading to sleep deprivation. Irregular work hours, such as those associated with being on-call, have been linked to an increased physical health risk. Being on-call can also impact social life and leisure activities, leading to decreased life satisfaction and increased psychological distress. The unpredictability and intensity of on-call work can lead to chronic stress, which can in turn contribute to burnout, depression, anxiety, and other mental health issues. So let us look at how alert analytics can help us reduce the burnout. Alert analytics is essentially reviewing the alerts periodically and giving feedback to the system to improve the quality of alerts. Have you ever wondered how many alerts your team is receiving? Which component or service is receiving most alerts? Or which is most noisy alert? Which medium is receiving most number of alerts? Is it chat, PagerDuty, or some ticketing tool like Jira? At what time the on-call was very noisy? And most importantly, how many alerts do not have it set up properly and are missing important things like priority, dashboard, runbook, or also called as alert references? A very few companies or teams do alert analysis. This is basic information which every on-call or the manager should have access to. Who would this be useful for? An on-call person who would be able to see which all alerts fired during their shift so that they can easily draft handover notes and not miss anything important. Managers to generate report out of these alerts to see the improvement over a period of time. Managers to understand how teams on-call is, if the on-call person is vulnerable to a burnout. Would also be useful for writing incident reports and see at what time the incident started or whether the alerts fired during an incident. So let's first understand the alerting stack and how to get this visibility using open source tools. At Cloudflare, we use Prometheus heavily. We have point of presence in more than 285 number of cities, and each point of presence have their own Prometheus. We have over 1,000 Prometheus servers. All these Prometheus send alert to Central's Alert Manager, and we have various integrations to route the alerts. We also route all the alerts to a data store for alert analysis. So this is life cycle of an alert within Prometheus. Prometheus collects metrics from configured targets at given interval. It evaluates the rule expression, displays the result, and can trigger alert when the alerting conditions are met. For example, when we configure to alert for disk usage more than 80%, it will initially be in inactive state. While it is evaluating whether the disk is full, it will be in pending state. And once the evaluation is done and the alerting conditions have met, it will be in the firing state. Once an alert goes in firing state, it will be sent to alert manager. Let's look at the core concepts of alert manager. When a firing alert is sent to alert manager, depending on alert manager config for the alert, it can inhibit the alert. So inhibition is something basically, inhibiting warning alerts with the critical alerts. For example, if a server is down, it doesn't make sense to alert for all the services which are down in that server, like Docker daemon down or Prometheus node exporter down when the server itself is down. So ideally, there should be just one alert, server down, and all the alerts related to that instance should be inhibited. This can be done by alert manager config. Alert manager can group alerts. If network partition occurs in a distributed system cluster, then instead of getting alert from all the instances in that cluster, alert manager can group the alerts based on group by conditions and send just one grouped alert. This way, the alerts are concise and keep the alert noise level low. Alert manager also provides a way to silence an alert during the maintenance or while the alerts are being worked on. And it routes the alerts to correct receiver integrations such as chat, PagerDuty, or ticketing tools like Jira or Zendesk. Alert manager, when configured properly, can mitigate a lot of alert noise. But that is not the case all the time. Not all alerts are configured optimally. Now we will take a look at how to analyze if the alert needs tuning. The alert in alert manager can be in either of 4 states. It can be in firing state, or inhibited, or silenced, or resolved. Alert manager sends notification for firing and resolved alert events via webhook integration. But alert manager doesn't provide notification for silences and inhibition via webhook integration. So the alert reporting we were doing so far were kind of incomplete. However, Alert Manager API does provide capability to query. So webhook will give us firing and resolved alerts, and Alert Manager API would give us active and suppressed or silenced alerts. So now the challenge was to merge the data coming from 2 different sources and in different formats. So correlating the alert is done using fingerprint, which is provided by Alert Manager Response. Fingerprint is a unique hash for the alert. It is basically hash of alerts label set. Alert Manager API also provides us fields which are highlighted in green, such as silenced by and inhibited by IDs, which is great. This would help us look up the silence details and inhibition details. So we decided to collect all of the Alert Manager states data using vector.dev instance and store it in a data store. Vector.dev by Datadog is an open source high performance observability data pipeline. It is written in Rust and is vendor agnostic. Vector supports a huge range of source to read data from and lot of sinks to write data to. It also provides mechanism to transform the data, like structure, change the format, or sampling, aggregation. So in short, we use vector.dev to collect data from source, transform the data, and write it in a data store. So here we decided to use vector instance, one HTTP server for receiving the Alert Manager webhook notification. We decided to use 2 vector instance HTTP client for querying Alert Manager API, alerts endpoint, and silences endpoints. And we are writing in ClickHouse data store using sinks. We have decided to use ClickHouse for storing all this data, but any other database can be used. The reason we're using ClickHouse is because a lot of data munging is possible in ClickHouse, like aggregating data while inserting using materialized views, or by replacing merge tree table engine, we can reduce the duplicate data. Also, ClickHouse supports join statements, which would be very useful because we are writing data in two tables, alerts and silences, and we would want to do the analytics based on these two tables. So we created, if we were to create individual columns for all the alert labels, the number of columns would grow exponentially, and with the addition of new alerts and unique labels. So we decided to create columns for a few selected labels which are important, like alert priority, instance, alert reference, dashboard, alert names, etc. And write all other labels as map of string, because we wanted to keep all the labels in the data store with minimal resource usage and provide an option for users to be able to query specific label or filter out based on a specific label. For instance, this labels map component is equal to ClickHouse. So we can either filter out or select these visualization based on these filtering. The downside of using map of string is that lookup for map is comparatively slower than string column lookup. We built multiple dashboards on top of this data, like alert name overview to drill down on a specific alert, at what time it fired, or how the pattern has been over a period of so many days. Alerts overview to get insight of all the alerts alert manager is receiving. Then alert overview by receiver. This is similar, but for a specific team or a receiver. Silences overview, to see the silences stats, the number of active versus expired silences, how long the silences have been active, and the longest duration for a silence. Then a few other dashboards, alert state timeline and Jira alerts overview. There were a couple of interesting finds. We found a few alerts which were firing and did not have notify labels set, which means the alerts were firing but were not being sent anywhere, creating unnecessarily load on alert manager. We also found a few components generating a lot of alerts, and when we dug up, it was for a cluster which was decommissioned, but the alerts were not removed. So these alerts were getting black holed, again creating unnecessary load on the alert manager. So these dashboards gave us great visibility and cleanup opportunity. So this is how an overview of alerts look like. It would show how many percentage of alerts are in firing or suppressed or resolved state, or which region is generating most number of alerts, or the alert pattern over period of time. We route alerts to teams, or a team can have multiple services or components. For example, alerts when it's being sent to observability team, who also owns multiple components like logging, metrics, traces, and errors. So this panel would give us alerting component count over time. This would be very helpful in identifying component which is noisy in a very quick glance. A good alert or properly configured alert should have clear information such as alert name, summary, priority, alert reference, and dashboard for it to be actionable by an on-call engineer and not get overwhelmed. We created some panels in the dashboard to list the alert names which did not have these important labels. When we silence alerts in Alert Manager, we can only provide matcher. The matcher could be anything. It could be exact match or regex. It could be alert name or any other label. The silence matcher doesn't translate to alert name or alert count. With this analysis, we can see which all alerts got silenced and with which silence ID by doing join queries on the two tables. We created this swim lane view using Grafana's state timeline panel for the receiver. This would give an idea about how busy the on-call was and at what point of time. Red here means alert started firing, yellow means the alert is active, and green means it has been resolved. So here we can visually see when an alert started firing and how long it was in active state and when it got resolved. It also helps in identifying the flapping alerts, as highlighted here. Flapping occurs when alert changes state too frequently. As shown here, it was in firing state, then resolved, firing, resolved. So it overwhelms an on-call because there's not much action to do. At the time you're about to do the work or you start to do the work, it gets resolved. It could be because of the alert which is not configured properly and needs tweaking, like adjusting threshold or increasing the for clause period in Prometheus. The for clause Prometheus is to wait for certain duration to make sure the alert is still continuing to fire, and only after that duration to set it as firing. This helps in reducing the flapping alert. This is another swim lane view with more number of alerts firing. So the rows here would be the alert which is firing and the columns would be the time. So here we can see at what point it was too many alerts were firing, and it's easy to identify. So the key takeaways for this talk are: make use of alert manager features like inhibition, inhibit warning alerts by critical alerts, use grouping. By default, all alerts are grouped by a route. So a group by field can be used specified to logically group alerts. Make sure the alerts are actionable and have all the important labels like dashboard and alert references. Make use of annotations in Grafana to correlate alert volume with incidents and releases. Last but not the least, do alert analysis periodically and give feedback to the system to improve the quality of alerts. So this is QR code for the link to AM2CH repo. It has a basic demo for alert analytics. Running Docker Compose up here would spawn up a few containers like Prometheus, Alert Manager, Vector, ClickHouse, and Grafana. And Vector would query Alert Manager API and write the data in ClickHouse. And Grafana dashboard has a demo dashboard, which would give few panels to give a brief idea about alerts overview. And with that, I would be ready to take questions.